I want to finish off our discussion about estimation by talking about what sets one way of estimation apart from another. In other words, how can we determine which is the better of two different ways of estimating an unknown quantity? And throughout our discussion on Unit 9, we've talked about the methods of moments way of making estimation, where we basically set the expected value of the PDF or PMF that we're working with equal to the mean and potentially standard deviation or variance of the sample mean and solve for it. And we've talked about the maximum likelihood way of estimating, where we write out the probability of observing our data based on the assumed probability model and figure out what value for that unknown parameter gives the resulting model the highest chance of producing the data that we've collected. So what really sets these two different methods apart from one another, and how can we make a definitive conclusion as to which way is better? And actually, not too surprisingly, is tied into what we consider what better is. And so to illustrate this, let's consider two people throwing darts at a dartboard. And I want to talk about which of these two people is better. So let's imagine we want to hit the bullseye right in the center of this, and our score is based on how far off the dart ends up being in any direction. The farther off we are, the lower the score. So person number one is going to be in red, and I'm just going to put a few dots for where this red person ends up making their shots. Sometimes they're pretty close, sometimes they're relatively far away. But on average, kind of looking at the distribution of where the red dots are, they kind of average out to be, right in the center here. So that's pretty good. Now, what about person number two? Let's choose green for them. And let's go ahead and make them a little bit thicker, actually. And what if the green person does something like this? What if, well, they're not really that close to the bullseye, but their shots are fairly concentrated, in a certain location on that dartboard. Let me go ahead and just overwrite these red persons. Which of these two people do you think is the better darts player? Is it going to be the red person that sometimes gets really quite close, sometimes really quite far away? Or is it going to be the green person who never really gets that close to the center here, but, never strays all that far either? So how can we talk about, meaningfully at least, which is going to be the better darts player? Is it player green or player red here? So what we need to come up with are ideas of what we refer to as the bias and the variance of an estimator. And these are going to be related to essentially how close the estimator's values get to the truth. When we take a sample and we try to estimate the unknown parameter, we'd like it to get pretty close to what the true value of that parameter is. And so let's flesh out some of this discussion. We'll come back to the bullseye in a little bit. So note number one, this section gets fairly mathematical. To actually come up with a numerical value for the bias, the variance, and the overall quality measure for an estimator, we have to do a lot of math. Now, and as an undergraduate in BAS 471, I'm not all that interested in having you be able to reproduce the math. That's more graduate level work. I mostly want you to be understanding the main concepts. What do we mean by saying an estimator is biased? What do we mean by saying an estimator has a high variance? And so we can run Monte Carlo simulations to come up with numerical values for each of these two different things. We're not going to worry much about where they come from, at least mathematically going through these calculations. So understanding is key importance. So we want to be talking about the quality of an estimator. What method of estimation is better than others? And so let's start out with a motivating example. So let's imagine that we are dealing with a random sample from a uniform distribution. The lowest possible value is 0, and the largest possible value is 2 times mu. Now, I've written it this way so that the average value of this uniform distribution, kind of right in the middle of the two endpoints, is mu. Mu is our universal symbol for the average of a PDF or PMF, and so that keeps that consistent. So our overall goal is that we want to use a random sample, some data values that we've collected, to estimate what mu is, what's kind of right in the center of that uniform distribution. And if we think about it, there's really no shortage of different methods we could propose as reasonable estimators, logical estimators of this center point. So one thing we could do is just take the data and measure the sample average. Well, mu is the actual average of the PDF, and so the sample average should get fairly close to that. And so that seems like a reasonable thing to do. And in this case, since the distribution is symmetric, the uniform is just kind of a flat line between 0 and 2 mu here, the sample median is going to get you there as well. The sample median is the value that's right in the middle of the sorted list of values that we've collected in our data. So since we're trying to estimate essentially that midpoint of that uniform distribution, the midpoint of our data seems like a reasonable thing to do as well. Another way we could do it is looking at the maximum value in our data. Now, the maximum of this uniform distribution is 2 times mu, and the maximum value of our sample is probably going to be pretty close to 2 times mu. So what if we took the maximum value, dividing it by 2, well, that's another logical and reasonable way of estimating what mu is. So 3 very reasonable ways of estimating mu in this case. Which one is better? Which one should I actually choose here? All right, well, let's think about the different properties of an estimator that we would like them to have. Number one, we would like the estimator to be unbiased. Going back to the dartboard here, these red dots, where these red players are throwing their darts, would represent kind of an estimator that is sort of unbiased. Sure, sometimes it's close, sometimes it's far, but kind of averaging over where the darts fall, we kind of land right in the center here, right where we want to be. The green player, well, their shots are a little bit biased. They're never that close to the center. They're never that far away from the center. They're kind of clustered a certain distance away from the truth. This would be a biased throw here. We expect to end up kind of far away from that bullseye. So let's take a look. Let's actually run a Monte Carlo simulation. Let's generate a whole bunch of random samples from a uniform distribution and just audition each of these 3 different estimators. And we'll see how close to each of these get to the truth. All right, well, in the unit9.r file, we have this Monte Carlo simulation. So what's going to happen, we are going to generate a random sample from a uniform distribution, a pretty small one, only 7 data points, and the values are going to range between 0 and 10. So in this case, we happen to know that mu by design is equal to 5, right in the middle of this uniform distribution. And so we'll have an idea for how far off each of these 3 estimators are on each of the samples we generate. So we'll create some empty vectors to create to store the sample mean, the sample median, and the sample max, and we'll run through that. So total of 10,000 different random samples being considered here. For each random sample, we've calculated the average, the median, and we've looked at half the maximum value. 3 reasonable ways of estimating this unknown quantity. And let's just look at the results. Let's make a data frame of these and look at a set of side-by-side box plots and talk about these. All right, so let me expand out this plot. And what are we seeing here? Well, each one of these box plots represents one of the 3 different ways of estimating this unknown parameter. Here's where we just took the sample average. Here's where we took the sample median. Here's where we took the max and divided by 2. And so what can we learn from this? Well, number one, the mean and the median are unbiased estimators of mu here. Sometimes the values are a little bit too high. Sometimes the sample average was, quite a bit above 5. Sometimes the sample average was quite a bit below 5. But on average, and that's where this red dot is, on average it, kind of lands right where we want it to be, right at 5 here. Now, the median is also unbiased. Sometimes it's a little bit too high, sometimes a little bit too low, but on average, where this red dot is, we're landing right where we want to be at a value of 5. So the mean and the median are what we call unbiased estimators. On average, at least, they hit it right on the nose. An individual sample might be a little bit too high, might be a little bit too low, but on average, right on the nose. Notice that the max estimator, taking the max dividing it by 2, yields a biased estimate. The average value here is always, or it's actually substantially lower than the truth at 5. And that makes sense. The maximum value is never going to get bigger than 10. 10's the largest value by definition in the simulation. And so the maximum value is always going to be a little bit less than 10. So the max over 2 is going to be a little bit less than 5 as well. So on average, yes, the max over 2 estimator comes out a little bit below our target, a 5 in this case, the truth. So is that the end of the story here? Can we just qualify the max estimator and say, well, just go for the mean or the median estimator? They're both unbiased. Well, there's more to the story here. Sure, we like to have an estimator being unbiased. Sometimes it's too high, sometimes it's too low, but on average it gets it just right. But there's a second component. If we're looking at and comparing unbiased estimators, say the mean versus the median, we can choose between these two by looking at which one gets closest, typically, to the truth. In other words, which values are typically a bit more clustered around the true value of that unknown parameter. So if we look at the distribution of these 10,000 different random samples averages, what we see is that the sample average, on average, gets it right, lands right at 5 here. And it's never that far away. Oddball samples, sometimes the average is getting close to 9, sometimes down to 1, but it's always within, give or take maybe 0.5 or so. Remember, in a box plot, 50% of the data values live inside this box. So about 50% of the time we're within, 5, give or take 0.5 or so, relatively close to the truth. Contrast that with the median estimator. Yes, it's unbiased. On average, it lands right where we want it to be. But notice over those 10,000 different random samples, medians that we looked at, we see a much bigger variation. It can be the case that the median ends up actually quite a bit farther away from 5 than what the mean was, and either above or below here, really close to 0 or really close to 10 here. So moving beyond this discussion of wanting to have an unbiased estimator, we'd also like to have an estimator with a relatively low variance. In other words, the possible values for that estimator that we might measure when we go take a sample are as tightly clustered around what the truth is. That's going to be what our main goal is. We want an unbiased estimator, and if there's more than one unbiased estimator, like what we see here, we want the one whose values tend to be clustered closest to the truth here. So in fact, there's even more to the story. Having two different measures is kind of a hassle here. We have the bias, we have the variance. People have combined these two quantities to come up with an overall measure of the quality of an estimator called the mean squared error, or the root mean squared error, which we're used to seeing in, say, BAS 320, 474, whenever we're doing some sort of predictive modeling. So what is this mean squared error referring to? We've talked about the bias, essentially, on average, how far off from the truth might we measure an estimate to be. We'd like to have an unbiased estimator. The bias is 0. But there's more to the story. We might have more than one unbiased estimator. We'd like the one with the lower variance here, the one whose possible values for that estimator are as clustered as closely to the truth as possible. So how have statisticians decided to combine both of these? Well, they've come up with a quantity called the mean squared error, squaring the bias and then adding the variance. That's going to be our one overall quality measure. If we were to take the square root of the mean squared error, that would be the root mean squared error, that RMSE that we've used in 320 and 474 to quantify the typical size of an error a model makes. And so what we're really after is the estimator with the lowest mean squared error. And that actually, and rather intriguingly, opens the door for the max over 2 estimator to be the better one overall. Because yes, it's biased. On average, it's coming in a little bit too low. It's a little bit below 5 here. But notice if we compare the variance of these 3 estimators, the variance of the max over 2 estimator is by far the smallest. Looks how skinny up and down that box is. It's pretty clustered around where its average is. And it's never that far away from the average here. Both the mean and the median in particular can end up with the value very far away from the average value of that estimator, but the max over 2 never really lands that far away from its average value. So since our overall quality measure combines both of these two things, the bias and the variance, it might actually end up being the case that the max over 2 estimator is the better overall. And, in fact, when we look at it in this particular way, if we go and look at the absolute values of the errors, now this is not the mean squared error, this is a slightly different variation, just looking at the absolute values of the errors themselves, you'll notice that if we look at the average absolute error, the max over 2 estimator right here has the lowest. Yes, it's biased, but on average, the absolute value of that error is smaller than the mean and the median. And so that's what we're going to turn to overall, is that when we're talking about the difference between two different estimators, we can talk about their bias. Are they both unbiased? If they're both biased, which one's smaller? We'd prefer no bias if given a choice. But there's more to the story. There's that variance. How clustered around the expected value of that estimator do we end up measuring values when we go and take data? Combining those two together, we're actually going to go for the estimator with the lower mean squared error. So if we want to choose between the two, we're going to go with the one with the lowest MSE. And in fact, there's kind of a holy grail that we look for when we do estimation, kind of as the funny acronym, the UMVUE, the Uniform Minimum Variance Unbiased Estimator. And what this is of all of the unbiased estimators out there, the one that has the lowest possible variance. In other words, if we consider only estimators that on average get it just right, essentially hit that bullseye right on average here, what estimator is going to get closest on average to that bullseye, closest to the truth? That's that UMVUE, the Uniform Minimum Unbiased Estimator there. And here is where the MLE really comes into play. So why do we prefer the MLE versus the methods of moments estimator? Well, it turned out that for very large samples, it has some very advantageous properties that the methods of moments estimator doesn't. So here's what we need to know about why we use the maximum likelihood estimator above all others most of the time. Now, especially for large samples here. So for a finite size sample, a few dozen or so here, the MLE might be biased, but you can show that, or mathematically, that as that sample size gets bigger, as that sample size grows off to infinity, that bias goes closer and closer to zero. So, in other words, as we're dealing with larger and larger samples, what we find is that the MLE is asymptotically unbiased, using super fancy math terms. So, in other words, it's a consistent estimator. The MLE, especially for large samples, is basically unbiased. Sometimes it's a little bit too high, sometimes it's a little bit too low, but on average, for large samples, it essentially nails it right on the head. There's no systematic bias making it come in too high or too small. Now, another reason we love the MLE is that we can actually talk about and develop a mathematical expression, in fact that's where we're headed next, of how far off we expect the value of the estimator is from the truth. We can predict the amount by which the MLE is off from the truth here. And using that, we can build confidence intervals. We can talk about the notion of a standard error. We have an idea for how far off the MLE is from the truth. Now, up until now, both those properties also apply to the methods of moments estimator. If you go and study the methods of moments estimator from a theoretical point of view, it turns out that for very large samples, yes, the methods of moments estimator is also unbiased, just like the MLE. It turns out that we can also predict how far off the methods of moments estimator is from the truth. We can leverage that and make confidence intervals out of there. But here's what sets the MLE apart. Of all unbiased estimators that are possible, the MLE is going to be the one with the lowest variance. So, in other words, when we go out there, propose millions of different possible ways of estimating an unknown value, if we only compare the unbiased ones, the MLE is the one that's going to get closest to the truth on average. And that's why we use it. So, in other words, as we're dealing with large samples, and large really isn't all that big in business analytics here, 50, 100 data points, that's what's needed for this theory to kind of kick in. And we almost always have that in analytics. As long as we're dealing with that large sample, the MLE is basically this holy grail of estimation, this uniform minimum variance unbiased estimator. And so that's what I want you guys to know to round off the discussion about estimation. There are ways that we can measure the quality of an estimator, namely its mean squared error. And if you just scroll through these notes, you can see there's a lot of math that goes in behind calculating these things, unless we want to write a Monte Carlo simulation. And so that's why we'll stick with just kind of knowing the basics here. So that holy grail is this uniform minimum unbiased estimator here, minimum variance. The MLE is that as long as we're dealing with a large enough sample. So let's see this in action, actually. I've been teasing you with saying, hey, the MLE is better than all these others. Let's bump up this sample size. For a sample of size 7, this bias is pretty noticeable. And I just said, hey, for large samples, the MLE is basically unbiased here. On average, it's going to get it just right. So let's see that. Let's go from a random sample of size 7 to a random sample of size 700. So in that case, the max is going to be pretty darn close to whatever the maximum value of that PDF is. So let's run this. This might take over in a jiffy. So we're ready to make the plot. And there we go. Impressive. I've actually never made this plot before, and I think this really hits this point home, is that for really large samples, notice how, okay, the mean, the median, still unbiased. Notice that sometimes the mean is really quite far away from the truth. We designed the simulation so that mu is equal to 5. Look how far away the sample mean can be sometimes, above or below. Look how much farther away that median is from the target here of 5. Sometimes it's really far away above or below 5. This max estimator, taking the max over 2, the average, this red dot here, pretty much right on target. And look how little variation we get. With a large sample here, we're almost on the nose to mu equal to 5 every time. That error that we're making is so tiny. Let's look at the distribution of the absolute values of those errors. Look at that. Look how much better we do by looking at that max over 2 estimator than the mean or the median estimator. There's a very clear ranking. So, taking this back to the bullseye example, which of these two dart players do you think is better? Is it the red dart player or the green dart player? The red dart player is unbiased, essentially. If we were to average out the locations of all these shots, it would land pretty much right on the bullseye. But the red player has a large variance. Sometimes it's really quite far away. Sometimes it's close. But the variance is pretty big. It's pretty far away from the average. Green player has a noticeable bias. They never get that close to the truth, basically the bullseye here, but they're never that far away either. So green is biased, but it has a relatively low variance here. So how could we make a decision? Well, we'd need to come up with some sort of score that kind of gives a compromise between, say, the bias and the variance of these darts here. And without that, written down mathematically, it's going to be a little bit hard to definitively tell, who's better, red versus green. It's going to depend a little bit on how you're gauging the overall quality here. So I'll leave that up to you to make up your mind. But that rounds out our discussion about how estimation proceeds. Now, there's a bit of tie-in, actually, back with BAS 474, with predictive modeling and how the predictive model was selected. If you think back to that class, when you were developing a predictive model, you didn't really care how well it fit the training data, the data that you already collected, because you already knew the answers to those individuals anyway. You want to know, well, which model is going to make the best predictions on as yet unseen individuals, new individuals that are going to be coming in our way. We want a predictive model that's going to get those people right, whose answers we don't know ahead of time. And so in 474, we were obsessed with coming up with a model with the lowest generalization error. If you really dig deep into the slides for 474, that generalization error is actually just a fancy term for the mean squared error of the model. The expected generalization error is the mean squared error. Same formula as what we saw in 474, the bias squared plus the variance, and when doing predictive modeling, some irreducible error that no model can really make smaller here. So these ideas are matching up. When we're doing estimation, when we're doing prediction, we want to get as close to the truth as possible, but there's two things that get in the way there. It's not just about the bias, on average, how far away are you from the truth, but it's also related to the variance. How tightly clustered are your estimates from the expected value? Since those two are being combined together, the overall best estimator, the overall best model, is really going to be the one that generalizes the best, the one with the lowest mean squared error, the one with the lowest root mean squared error here. And so you might remember this is one of the more famous slides in 474. What happens as we make our model more and more and more complex? Well, as we increase the complexity of the model is going to be able to fit the subtleties, the quirks, the weirdnesses of any relationship out there. As the complexity increases, the bias of that model is going to get smaller and smaller. It's more flexible. It's able to model a pretty complex truth. But here was the rub. Here was the catch-22. The more complex we made that model, the more information we had to extract out from our data, the training data. And the more information we extracted out from that training data, the more we made the model's form sensitive to the particular set of individuals that just happened to be collected in our data set. We measured that sensitivity by the variance of the model. So as the model became more complex, its form became more sensitive to the individuals in the training data. The variance, how much it could change if we switched up that training data, gets bigger and bigger. Adding these two things together, well, we had this curve talking about that mean squared error, the expected generalization error of the model, and we knew there was a sweet spot. There was an optimal amount of model complexity we wanted to throw in, and that's what that carrot package was designed to help us out. Try out all these different ways of building the model, estimate the generalization errors of each one of them, and choose the one with the lowest estimated generalization error. All right, that's a wrap. We'll see you in Unit 10.